Welcome learners to the course on MOS Capacitor. Myself, Orpon Deasi, from the Department of Electronics and Telecommunication Engineering, RCC Institute of Information Technology, India. Welcome you all to the course on MOS Capacitor. So, today, before going to the details of the course, let me first tell you that in the 21st century, in the year of 2020, we are more or less surrounded by MOSFET based devices from day to night, the 24 hours. So what is MOSFET? Why we are surrounded with it? Let me recall with all the devices, electronic gadgets we are using, from our smartphone to laptop to desktop. So air conditioning machine to washing machine, micro oven, everywhere, television, refrigerator, every building block is the MOSFET. So today the journey of MOSFET and MOSFET, everything requires a solid foundation, a beginning. But let me differentiate the two terms. Today we'll start with the MOS, not MOSFET. So you may have a query that what is the difference between the MOS and MOSFET you are dealing with. I will go to everything detailed step by step, the physics, the basic foundation on which you will build your monument later on. But let me start with the foundation of today's course on the MOS capacitor. So just give me a pictorial representation of today's world, how it really looks like. So for that, I'm starting with the foundation of the fabrication. You know that every device has to be built based on a wafer. What is wafer? It's a very thin plane of the semiconducting material, has a 12-inch diameter nowadays, started from the 3-inch diameter, then 4, 6, 8, and now the 12-inch diameter. All the devices will be based on the wafer, based following different fabrication methodologies. But today our course will be not on the fabrication technique, so I will be totally based on the foundation level. Just give a glimpse, just make you rotating how the things are going on. So on the top of this wafer, if you have a wafer, if we try to build a device, we will get its characteristics. A digital device, normally we know the plug in and plug out in our day-to-day life. So a digital device should have a on condition and off condition. So naturally the devices, the MOSFETs which will be based on built on this basic wafer should have a on and off condition. And once we get this on off condition, then we will have a its symbolic representation, like the how the MOSFETs will look like, and I am giving you the blue blocks inside the symbolic representation of the MOS transistors. Now once you will get symbol, you want to know what will be the details inside. I think in your undergraduate course you have a familiarity with the MOSFET, so with based on that assumption, I am giving you a pictorial representation of a device maybe called as a MOSFET. So from symbol I am giving to the device MOSFET, as well as from the device I am giving you the array of the devices, the combination of the N and P that will be considered as a CMOS, that means the complementary MOSFET. Every digital devices will be based on the CMOS concept, but once we go for the analog, there will be no requirement of the CMOS. Maybe it's a combination of P and N, but doesn't have to make us PMOS. So for digital design, I am giving you a CMOS perspective, and today's information age, you have to store all the data. So once you have to think about the storing of the data, you require some sort of memory devices. So for memory devices, you have to build the founding memory, that means the DRAM and the SRAM. What are those? The dynamic random access memory as well as the static random access memory. I am giving you a pictorial representation of a dynamic random access memory. Basically, it's based on the combination of the CMOSs or different sort of MOSFETs. So from memory, why I'm going to memory? That is because of the memory storing element, the data storing things. And the combination of the different memory and other sort of complex circuits ultimately gives you a planar completely complex circuit. It may consist of the billions and billions of the transistors. And these billions and billions of the transistor can be called as a integrated circuit. The first integrated circuit, this is the packaged form of the integrated circuit. The first integrated circuit developed by Jack Kilby in the year of 1959 onwards, and whose name is basically given a JK flip-flop, I think you may know. So it's a 60 years before. From that, the journey may onwards going on towards today's revolution. So that's the integrated circuit. And integrated circuit combination ultimately gives you the next figure. I think everybody knows the next figure, that is called a processor. So processor is the heart of today's everything. Whatever the electronic gadgets you are using, the core thing is the processor. So you are getting the symbolic representation of the processor, and the processor, from that the next diagram, I think nobody has to tell. A 3 years old child can say it's a laptop. So it's known to all. Every household now today have a laptop. So I am giving you a simple journey from a basic device material, from the wafer to the ultimate system. So that's the journey. And if you have to go inside the journey, you can go in two ways. One is the theoretical foundings, the analytical people who are making the theoretical research. Another is the experimental people who take the design from the theoretical people and can make the devices. So, but whatever, if you have to go for theory or if you have to go for the experimental way, you have to know the foundation on which you can build your empire. So, for the foundation, you have to make a journey based on your prerequisite, the basic knowledge of physics, material science, mathematics, the carrier transport phenomena. Everything will come into the effect of today's class. So, if you like these things, we will go for progress of this. So, but before making on this the next level, I am giving you another important concept. Maybe in our undergraduate course, knowingly or unknowingly, unintentionally, we write MOS and MOSFET at haphazard times, and we generally assume that MOS and MOSFETs are same, but that's not true. That's not really true. MOS and MOSFET are not really same. They are completely different. Let me go into the little bit more details. What do you mean by term MOS? It's metal, oxide, semiconductor. And what do you know by the MOSFET? It's metal oxide semiconductor field effect transistor. So at that time, you may think that what is the fate? Why, if I write fate or if I don't write fate, what matters really? It really matters. MOS and MOSFET are not entirely same thing. It's totally worldwide, it's different. So at this juncture, before going to the depth, before going to the ultimate package product from the wafer level, to make the journey, we have to know what are their differences. What is the valuable differences lies between the MOS and MOSFET. So for that, I am asking the question, are MOS and MOSFET same? From now onwards, our answer will be no. You may think, why? Why people are saying, but naturally we use both the terms. Even some textbooks also write somewhere it is MOS and giving a symbolic representation or meaning it's a transistor, but it's not the same. So, with this basic journey of what is happening around us, we have to go to the world of MOS today. Please remind again to all of you, it's not world of MOSFET, it's the world of MOS. But before going to the world of MOS, let me go into slightly more deeper level, more foundation, where I have to start with the terminology called MIS. Now let me ask the question, what do you mean by MIS? M stands for metal, S stands for semiconductor. Now, why you are talking about the term oxide? Why you are taking the term oxide? Because you want to put a dielectric, an insulator there. So if you have to mention all the materials, in terms of their conducting properties, why you are going for the oxide in terms of electrical properties, you have to make it synchronous. If you want to make everything synchronous, that means all the materials you are using has to be synchronized while describing in terms of their conducting properties. So we will take the conducting property of highly conductive material means metal, so M. Conducting property of moderately conductive material, that's semiconductor, S. And conducting property of very less conducting material, that is insulator, I. So fundamentally the structure will be called MIS, not MOS. It should be MIS. So let's go details from the fabrication point of view how a MIS structure is grown. Let me show you. Take a semiconducting substrate. It's shown in the figure as a yellowish block. You can make it grow by MB, by CVD, by MOCVD, whatever the technique you like. It's a semiconducting substrate. Now on top of which you are making an insulating layer. A simple insulator is grown on the top of semiconducting substrate. So it's now a bilayer structure. Is it clear? It's a bilayer structure. Insulator, semiconductor. Now I am trying to make it tri-layer. How? I am making another conductive layer on the top of insulating layer. So what is happening? I am getting a tri-layer structure, metal, insulator, semiconductor. They have different conducting properties. Metal has the highest conductivity, insulator has the lowest conductivity, and semiconductor are between them. Now in that point, just think about applying bias. Let's say metal side is positive and semiconductor side is negative, or you may rotate it. Doesn't matter. So if you apply bias, what will happen? Now think, you have two conducting materials. Maybe they have same conductivity, maybe they have different conductivity, and a dielectric is sandwiched between them. So recall your school level class of basic electrical, where you have started the concept of the capacitor, and at that time you said that the capacitor is a material with two conducting layers and the insulating layer is sandwiched between them. If you have a problem in visualization, rotate it 90 degree, then I think you may synchronize with your known capacitor format. I am talking about the parallel plate capacitor. So a MIS structure, when have applied bias, and bias can be made only the outer side, so it has only two leads. So MIS structure works like a capacitor. Now please think, it's not a MOS, it's a MIS. And recall your earlier courses on transistor. What are the transistors? It requires at least more than two biasing contacts. But how you can get more than two biasing contact in a tri-layer structure here? You can't give bias to an insulator, it's of no use. So you can give bias to metal and semiconductor, and you will get a device with two terminals. Now two terminal devices are resistor, capacitor, diode, inductor, and like those things. Out of which this MIS structure works as a capacitor. Fine. So MIS is nothing but a capacitor. Now please try to replace or make it a special type of insulator, say oxide. If you replace this insulator, or say make a specific nomenclature of this insulator as the oxide insulator. Then the term I will be replaced by O. And if I is replaced by O, then it will be called MOS. So MOS is nothing but a special type of MIS device which works as a capacitor. The only difference is that, or only speciality is that, there is no other insulator but has to be an oxide material. So MOS is a special type of MIS, and please now consider my earlier statement. MOS is not a transistor, it's a capacitor. So once you get this, then you can say what are my materials we will use for day to day, because end of the day you have to go for practical perspective, you have to look onwards. So the convention is you have to choose normally aluminum as metal. At that point, I may remind you, don't consider aluminum is used because of its cost effectiveness. No, that's not the important point. That is one of the points, but there are some other major factors based on the electronic properties of aluminum. I will come a little bit later on. So convention is metal is aluminum. Insulator normally used as a silicon dioxide, which can be very easily grown on a silicon substrate. So aluminum silicon dioxide silicon is my device where the term metal starts with the term M, oxide starts with O, and semiconductor starts with S. So combination will give you MOS, and it is a capacitor. So MOS is a capacitor, and from now onwards, I will go with aluminum silicon dioxide silicon system. So let's today make the journey in the world of MOS, not to the world of MOSFET. So the question will be, we have to understand the electronic properties of this capacitor, how it really behaves. And from our undergraduate level course, we know that if we have to learn its electronic properties, we have to understand its band diagram very carefully. And remind again, MOS is a heterostructure. The question will be why it's a heterostructure? Because metal, insulator, and semiconductor, they don't have same band gap. You know that insulator has the highest band gap, semiconductor has moderate band gap, metal has almost zero band gap, so there is no band gap, better to say. So if different materials, different with respect to the property of band gap, make a device, or better to say make a junction at first, it should be a hetero junction, it's not a homo junction. If you have further queries based on that, we can start with the two fundamental properties. Those are derived from the Mendeleev's periodic table, and we can start with from that point of view. So I am giving you two very important concepts of work function and electron affinity, which are derived from the Mendeleev's periodic table. Let's take a semiconductor and say the highest level is my vacuum level, which is E equals to 0 line. Now, if you want to liberate an electron from conduction band to vacuum level, that means to E equals to 0 line, the amount of energy required is called electron affinity, denoted by the symbol chi. Whereas the amount of energy required to liberate the electron from Fermi level to vacuum level is called work function, denoted by the symbol phi. So naturally, if from the diagram you may find that phi is always greater than chi. Not necessary. I am going into little bit more details. So normally we know that work function is greater than the electron affinity. And I am drawing the diagram of a non-degenerate semiconductor. You know what is non-degenerate means? Non-degenerate semiconductor means the forbidden, inside the forbidden region Fermi level should lie. Now think about the case of a degenerate semiconductor. If it is a p-type degenerate, then Fermi level will go inside the valence band. If it is n-type degenerate, then Fermi level will go inside the conduction band. Now p-type degenerate, we have no problem. Work function will be much longer, it will be greater than electron affinity. But if you look about an n-type degenerate semiconductor, please think, just try to visualize, Fermi level will be less than electron affinity. Now there is the question. So phi is always not greater than chi for semiconductor. Normally phi is greater than chi, but for n-type degenerate semiconductor phi is less than chi. Recall your school level class of photoelectric effect, Einstein's photoelectric equation. At that time, we consider work function and electron affinity as synonymous. Why? Because you deal with a metal. For metal, Fermi level and conduction band are same. So whatever be the electron affinity, that will be the work function. So phi equals to chi for metal, but for semiconductor it is different. For non-degenerate semiconductor, phi is always greater than chi. For p-type degenerate semiconductor, phi is greater than chi. For n-type degenerate semiconductor, phi is less than chi. Based on that, I will try to differentiate between a Homo junction and a hetero junction. So let's go to that. So what is Homo junction? Homo junction is a junction where in either side of the junction, the material will be same. That means the band gap of either side of the junction will remain same. Now take a PN junction, which is very known to all of us from our high school level. For a PN junction, you know that Fermi level is close to valence band for p-type semiconductor and close to conduction band for n-type semiconductor. So if you have to draw the band diagram of a Homo junction device, you have to align the Fermi level, and that means you will get a difference of conduction band between p and n-type as well as the similar difference of valence band between p and n-type. The difference of the conduction band is called built-in potential. Please remind, the difference of the conduction band or the difference of the valence band for a Homo junction is called built-in potential. And since in either side of the junction you have the same material, so the electron affinity will be same. That means you have to bend the vacuum level also. So in Homo junction device, only Fermi level is constant, vacuum level, conduction band, intrinsic Fermi and valence band all are bending. And remind, all are bending with the same radius of curvature. So that's one of the phenomenological difference. We have to remember that all the bands will bend except the extrinsic Fermi level for a Homo junction device. So what will be the hetero junction? For a hetero junction device, the situation will be different. Now consider the hypothetical orange vertical line. It's a hypothetical line, just I am drawing to illustrate it. In either side of the vertical line, you have two different semiconductors, semiconductor A and semiconductor B. Semiconductor A is denoted by two blue lines, which are conduction and valence band. Semiconductor B is denoted by two green lines, conduction and valence. And we have chosen for this specific example, band gap of semiconductor A is less than the band gap of semiconductor B. And you know that if band gap is less, generally its electron affinity will be larger. So now I am following the Anderson's rule to draw the heterojunction. What is Anderson rule? That if you have different materials, then you have to align the vacuum level. So if I draw the constant vacuum level, which is shown at the dotted line, orange dotted line, horizontal line at the top, then you will get two different electron affinities chi A and chi B for semiconductor A and B respectively. Then the difference of the electron affinity will be the difference of the conduction band. It's clear from the figure. So conduction band difference for a heterojunction depends on the difference of the electron affinity, whereas for a homojunction, it depends on the alignment of the Fermi level. So now there is a significant difference between the homojunction and heterojunction. I am just zooming it more so that you can understand it quite better. So you will get the difference of the conduction band, which is known as delta EC. It depends on the chi A minus chi B. So I am coming out exactly the same format as shown below. Again, you have a difference in the valence band, which will be called valence band discontinuity. Why it comes? Now look, there is a difference of the band gap, say EGB minus EGA. That band gap difference is the summation of conduction band discontinuity and valence band discontinuity. Now conduction band discontinuity depends on the difference of electron affinity. So valence band discontinuity is a function of band gap difference and electron affinity difference. And obviously conduction band and valence band discontinuity should not be same. Whereas for a homojunction, both should be exactly equal. So that gives another significant difference between the homojunction and heterojunction. The discontinuity in conduction and valence band for a heterojunction are different whether it is exactly same for a homojunction. So that gives us the concept of heterostructure and homostructure. Now we have to proceed for the heterostructure. So for that purpose, we have start with the band diagram of a MOS. I am taking aluminum, silicon dioxide and N-type silicon for example. Now first I will draw the bands in a discrete manner. Then I will try to merge them as a system and apply bias, and we'll try to find out what is happening really inside. So for diagram, let's first draw E equals to 0 line, that is the vacuum level. Now I am going to the metal side. So metal side I am drawing the blue line, which is my Fermi level. And we know for aluminum, the electron affinity is 4.25 electron volt. So that's the difference of Fermi level or conduction band, whatever you can say for a metal, it's synonymous. So difference of Fermi level to vacuum level. That is for aluminum. Next comes to the silicon dioxide. Silicon dioxide has a wider band gap and the band gap is 8.76 electron volt. So it's an insulator. From the band gap it is very clear, and electron affinity is very small, it's 0.9 electron volt. So that's the band diagram of silicon dioxide, and obviously Fermi level will lie at the middle because it's an intrinsic, so I am not bothered about the electron transmission from valence to conduction, doesn't matter. And I am now going to the silicon. Silicon, the conduction and valence are showing by the two orange lines, EC and EV, and their band gap is 1.12 electron volt, everybody knows about that. Now, the electron affinity of silicon is 4.05 electron volt. Now match with the electron affinity of aluminum. The difference of the electron affinity of silicon and aluminum are very, very close. Please look at here. So there will be a very close matching. In respect of transmission of electrons from the Fermi to or the conduction band for a silicon, so conduction to vacuum level are requires almost equal amount of energy. That's one of the major thing people choose aluminum. Now it will be different for the polysilicons nowadays, but I will come a little bit later on. So choice of aluminum as a material, obviously low cost is a matter, but choice of aluminum as a material for this purpose. So that's the band diagram of aluminum silicon dioxide, and N-type silicon means Fermi level will be close to the conduction band. If it is P-type, Fermi level will be close to the valence band. So that gives the schematic representation of the band diagram, but remind it is the band diagram under unbiased condition for a MOS structure where M is the aluminum, O is the silicon dioxide, and S is the silicon. It may be N-type or P-type, just it will vary the work function, nothing else. So that gives the pictorial representation of the band diagram. I am showing the aluminum, silicon dioxide, silicon. So that's my complete representation of the band diagram, but that won't give you current or any electronic property because you have not applied bias till now. So if you want to apply bias, how it really will change? Let's go for that. So after unbiased condition, we have to think about how the band diagram will change if we apply the bias. Now, application of bias has multiple ways. What are the ways? You can apply positive bias at the metal side. That's the pictorial representation. Positive metal means semiconductor will be negative. Or you can apply negative bias at the metal side, that means semiconductor will be positive. So both the things are possible. You can switch the polarity of your battery. Both the things possible. You can apply positive bias to the highly conductive material or negative bias to the highly conductive material. But at this point, please think, your semiconductor can vary its property based on the doping. Actually, based on the nature of doping. What is that? You can take aluminum silicon dioxide silicon of N-type. So, in that case, you can apply positive bias at the metal side and you can apply negative bias at the metal side. Similarly, you can take aluminum silicon dioxide silicon P, for which positive bias at the metal side and negative bias at the metal side. So there are 4 different options. Today we will cover the aluminum silicon dioxide silicon P-type with both positive and negative bias variations, and that will give you the idea if semiconductor is N-type, what will be the biasing variation. So I am going to start the biasing variation on aluminum silicon dioxide silicon P-type, and why I am taking P-type, that will be more clear once we go to the first class of the MOSFET. So I have to start. Now, the first figure which is shown in the left hand side, it gives you metal, semiconductor and insulator at the middle, that is sandwiched with different values of the energy, the chi and phi and everything is given. So that's the composite band diagram what we have considered at the unbiased condition. I am showing the same figure. There is nothing new, so I am not discussing it in more details. Now come to the case of application of bias, and I am trying to start with a voltage less than 0. That means I am applying metal side as less than 0. So how it will be? Please think now. If you apply metal voltage negative, then the semiconductor side will have a positive voltage. Is it clear to all? That means electrons in the metal will be repelled and holes in the semiconductor will also be repelled. Now it is a p-type semiconductor, which means holes are majority carriers. So consider a hole in the valence band. Now you are applying a force to it by virtue of the bias. So if you push that, the hole can maximum go to oxide semiconductor interface because it can't penetrate to the oxide layer. So if it goes to the oxide semiconductor interface, then what will happen? You are making more and more holes in the oxide semiconductor interface. That means you have a major hole density at that part. Now in a normal p-type semiconductor, at a particular region, you are increasing the hole density. So if you increase the hole density, that means what you are doing, you are making it more p-type. So if you make the semiconductor more p-type, either Fermi will come to the valence band or valence band will be bended towards the Fermi level. Now we know that extrinsic Fermi level is constant. So what we have to do, we have to bend the valence band towards the extrinsic Fermi level. So the gap between extrinsic Fermi level and valence band decreases, and since valence band bends, so the conduction band and intrinsic Fermi level will bend in upward direction with the same radius of curvature. That means conduction, intrinsic Fermi and valence band all will bend upwards. So at this condition, you are also bending the insulator band diagram. The question will be why? Now think. At that point, insulator band will be bended in such a way that in metal side it will be higher and the semiconductor side it will be lower. The question will be why? Because you are pushing the metal electrons towards the junction, so the insulator band will be bended in such a way that these metal electrons should not be able to surmount the potential barrier and can go to the semiconductor layer. So that means you have to make a barrier higher in the metal oxide junction compared to the semiconductor junction. So insulator band diagram is also bended towards the metal side. So you will get a modified insulator band diagram as shown in the figure. And that condition is known as accumulation. Why? Because you are accumulating the majority carriers in the valence band of semiconductor oxide junction. So if you apply metal voltage negative in a aluminum silicon dioxide silicon P device, then you will get majority carrier accumulation at the oxide semiconductor interface in the valence band of the semiconductor, and that accumulation of the majority carrier causes the phenomenon nomenclatured as accumulation. Next, if we go for a different application, the same band diagram, now we are considering metal voltage positive and small. If that happened, this is the same structure. Now look, if metal voltage is positive, it's all electrons are pulled. I have no problem. Now remind, I am not going to the Fermi level of the metal side. It will be pulled up or down, but it can be clarified a little bit later on. So If you just push the electrons or push the electrons in the semiconductor side towards the junction, what will happen? Please think. Now, you are giving negative voltage at the metal side. So negative voltage at the metal side means you are pushing the electrons towards the junction. How it will be? This green ball, considered it's the electron in the conduction band. You are giving a force. So if you give a force, it will go towards the interface of the oxide semiconductor. Now, this is a p-type semiconductor. You are making more and more carriers in the oxide semiconductor interface, which are minority carriers. Now, if you make minority carrier accumulation in an otherwise whole majority dominant structure, then the concentration or the effective concentration of majority carrier at the oxide semiconductor interface will be decreased. So, what will happen? It will become less p-type. Once it will be less p-type, what will happen more? That due to the factor, the bands will bend downwards. Why? Because less p-type means the gap between Fermi level and valence band will increase, and Fermi level is constant, so valence band has to bend downwards. If valence band bend downwards, then conduction band and intrinsic Fermi level will also bend downwards. So all the bands are bending downwards and we are getting the downward band bending. So it is just the opposite type of band bending with respect to the accumulation condition. Now, what will happen to the insulator band diagram? Please think. I am showing that insulator band is now tilted towards the metal side and it will be rises up in the oxide semiconductor interface. The question is why? Since you are sending more and more electrons to the oxide semiconductor interface, so you have to prevent those electrons in order to surmount the barrier and then go to the metal side. So the capacitive action will be lost. So you have to raise the potential barrier in the oxide semiconductor interface, and if you raise the barrier in one side, in another side it should be decreased. So that will be the shape of the insulator band diagram for the condition when metal side voltage is positive but small. And since this condition gives you the accumulation of minority carriers, so that's why the condition known as depletion condition. So I think with this logic, you have cleared the cases of accumulation and depletion. Let me summarize these two cases before going to the case number 3. In accumulation condition, bandit bends upwards because of the accumulation of majority carriers in the oxide semiconductor interface. In depletion condition, bandit bend downwards due to the accumulation of minority carriers at the oxide semiconductor interface. Number 2, in accumulation condition, because you are giving negative voltage at the metal side, that means positive voltage at the semiconductor side, so metal electrons are pushed so that Fermi level of the metal side will increase, whereas in depletion condition, Fermi level of the metal side will decrease. I am not showing the animation of the Fermi level because it doesn't matter for our MOS capacitive purpose, but once we go to the other cases, we have to show the Fermi level variations. Now I am mostly dealing with the insulator and semiconductor band diagram. So that's the variation for the depletion condition. Now I will come to the most interesting case, which will be measured with respect to this depletion condition. So, in that case, I am showing another point. The difference of intrinsic and extrinsic Fermi level is called Fermi potential, that is psi f. and the bending of the band, that means bending of the intrinsic Fermi level with respect to the reference line, is called surface potential. Now, if you recall the measurement of surface potential for both accumulation and depletion condition, you will find that both are small compared to the Fermi level. Look here, because if you have to make it, then the intrinsic Fermi level has to touch the extrinsic Fermi level if you have to make them equal. But since intrinsic Fermi level can't touch the extrinsic Fermi level, naturally surface potential is smaller compared to the Fermi potential for both accumulation and depletion condition. That is given as the psi f and psi s, given in the pink color and shown in the arrow. Now I am going to the third case. The left hand side figure is shown already for depletion condition. Now take this depletion condition and increase the bias. That means metal voltage will be more and more positive. What will happen? You have already some electrons at the oxide semiconductor interface. Now you are giving more negative voltage to the semiconductor side. That means more and more electron will be forced to go to the oxide semiconductor interface. So that means if you give more force, the band will be bended more. If band is bended more, that means what will happen at a time, the intrinsic Fermi level may touch the extrinsic Fermi level. At this point, please visualize it more clearly. Because of the more accumulation of minority carrier at the junction, intrinsic Fermi level bends more downwards and it touches the extrinsic Fermi level. So, what will happen? You will get the point where the both Fermi levels will touch, and at that case, this point is called point of inversion. Now you may ask why the inversion term is given. I will go to that clarification at just a few minutes later on. But please remind, at this case, intrinsic Fermi level and extrinsic Fermi level, they just touch. And if they touch, then obviously if you increase more potential, what will happen? More carriers are coming, so band will bend more. And if band will bend more, then intrinsic Fermi level crosses the extrinsic Fermi level. Now please consider what will happen if intrinsic Fermi level crosses the extrinsic Fermi level. If they cross, then at this point you will find a small portion where you will get that a condition which will be called inversion condition. The question will be why? Because if intrinsic Fermi level goes below the extrinsic Fermi level, then extrinsic Fermi level at that case will be closer to the conduction band. If it is closer to the conduction band, then what will happen? It will behave as an N-type semiconductor instead of a P-type semiconductor. Because in P-type semiconductor, extrinsic Fermi level will be closer to valence band, whereas in N-type semiconductor, extrinsic Fermi level is closer to conduction band. So if extrinsic Fermi level becomes closer to conduction band, it will behave as an N-type semiconductor. That means a P-type semiconductor becomes N-type without further external doping, and that's why it is called, the condition is called inversion. Now recall the case when both the Fermi level touches, so it tries to make it invert, and that's why the point is called point of inversion. So that's the most important part of this analysis, how the inversion occurs in a aluminum silicon dioxide silicon p-type device. It may happen for a silicon n-type device, just the band will be bended in a different direction. If it is downwards, at that case it will be upwards. So we will get the condition of inversion where I am showing now surface potential becomes greater than the Fermi potential, because surface potential gives you the measurement of total amount of bending of intrinsic Fermi level, whereas Fermi potential is the difference between intrinsic and extrinsic Fermi level. Since intrinsic Fermi level crosses the extrinsic level and goes below, that's why surface potential becomes greater than the Fermi potential. So in inversion condition, surface potential is greater than the Fermi potential. Please remember this point for further analysis. So what I am finding as a for these three analysis, we find that for accumulation condition, surface potential is less than Fermi potential and surface potential is negative. For depletion, it is less but both are positive. At point of inversion, surface is equal to Fermi potential. At case of inversion, surface potential is greater than Fermi potential. These boundary conditions are extremely important when we go for the analysis of the MOS capacitor. So, what will be the bending of the band? In accumulation, it will be upward bending. In depletion, it will be downward bending, but EFI should not cross EF. In point of inversion, EFI will touch EF and downward bending. And for inversion, EFI will cross EF and it will be downward bending. So that gives the total variation, the band bending and the surface and Fermi potential relation for accumulation, depletion and inversion condition. At that point, we stop here and we will show you some selected references from where the concepts are derived. You can go for the textbook. Textbooks are most essential. The lecture will be uploaded in my YouTube channel, and for your later clarification you required. And from the next day, we will start with the concept of the surface and Fermi potential relationship that will give you our mathematical calculations for deriving the electrical properties of this MOS capacitor. And we obviously start from the concept of the depletion and inversion. We have a make a short recapitulation and we look forward. And from that, once we cover the MOS capacitor, then from this inversion concept, we will try to derive the case of MOSFET, that means the transistor. So that's all for today. Thank you for hearing me.